Part 2 of Unit 6 is about Lewis structures. A Lewis structure is a representation of a molecule that shows all the valence electrons bonding and non-bonding. So it shows all the covalent bonds that exist in a molecule and all the unbonded valence electrons that are left over. If you think about a hydrogen atom has one valence electron, and if two of them were going to bond together like they often do, those two electrons would be shared to form a single covalent bond. So this line right here represents one covalent bond, which is two total electrons, one from each hydrogen. If you think about a chlorine atom, each chlorine has 7 valence electrons, and it's also diatomic, so it's also going to form this bond very often. So our Lewis structure for Cl2 would have to show all 14 total valence electrons. We've got our 2 from the bond between the two atoms, and then 4, 6, 8, 10, 12, 14. So all of the 14 valence electrons from both atoms are shown in that Lewis structure. You may want to pause this and take a minute and write down the rules for drawing the Lewis structure of molecules. First thing you need to do is find the total number of valence electrons of all the atoms in the polyatomic ion or molecule. If it's an anion, you add 1 electron for each negative charge. If it's a cation, you subtract 1 electron for each positive charge. So if it's got a negative charge, we have to add more electrons. If it's positive, we have to subtract electrons. The central atom is the least electronegative element that isn't hydrogen. Hydrogen's never going to be your central atom. You're going to connect the central atom to the outer atoms by drawing single bonds that represent 2 electrons. The next step is to fill out the octet of the outer atoms. That means you want to draw dots or valence electrons around them so that they have 8 total valence electrons, counting the bond that you've drawn to the central atom. And if you run out of electrons before the central atom has an octet, or before the central atom has 8 electrons around it, you need to move unbonded electrons to form multiple bonds until it does. So if we were going to look at phosphorus trichloride, PCl3, our first step is to add up the total number of valence electrons. We've got 5 from phosphorus, and we know that there's 7 from chlorine atoms, and there's 3 of them. So we've got 7 times 3 is 21, plus 5, that's going to be 26 total electrons that we have to draw in our Lewis structure. Now, phosphorus is going to be our central atom because there's only one of it, and it's going to be surrounded by 3 chlorine atoms. Now we need to connect these atoms together, so we're going to draw a line representing our single bonds, and that takes care of 2, 4, 6 of our electrons. Now we need to go through and fill out the octet for the surrounding atoms. So we'll put 1, 2, 3, 4, 5, 6 dots around this chlorine. That gives it a total of 2, 4, 6, and 8 electrons just around chlorine when you count the bond there. And we'll do the same thing to the other chlorines. So total, we've drawn 8, 16, 24 of our 26 valence electrons. What we need to do with the last 2 is put them on this central atom. That way all the chlorines have their octet filled. They've all got 8 valence electrons, and so does phosphorus. It's got 6 from the bonds and then the 2 unshared electrons. And all the atoms are happy now. Everyone's got their octet. That is the Lewis structure for phosphorus trichloride. Let's look at another one, hydrogen cyanide. Hydrogen cyanide is HCN, hydrogen in the cyanide polyatomic ion. Let's add up our total number of valence electrons. We have 1 from hydrogen, 4 from carbon, and 5 from nitrogen. So that gives us a total of 10 electrons that we have to draw. Hydrogen's never going to be our central atom, so we're going to have HCN. We'll just write this one in order. And now we need to connect the atoms together. So we've drawn our bonds connecting everything together. Now we need to fill out the octet on the surrounding atoms. Hydrogen is already happy with these 2 electrons. Hydrogen doesn't take 8 valence electrons, it can only have 2 because it only has a 1s sublevel. That's only got room for 2 electrons. So hydrogen is fine the way it is. We need to go and fill out the octet for nitrogen, however. So it's 2, 4, 6, 8 electrons around nitrogen. Now, we've drawn 2, 4, 6, 8, 10. We've drawn all of the electrons that we can. However, there's not 8 electrons around carbon. So what we need to do is move some electrons and create a multiple bond. So what we'll do is take these 2 electrons from the top of nitrogen and we'll move them over and share them with carbon. Nitrogen still has an octet, and carbon's closer to having one. It's got 6 electrons. So we'll do the same thing with this bottom set of electrons. Move them over and share them between nitrogen and carbon. Nitrogen has its 8 valence electrons, and now carbon does as well. So we formed a double bond and then a triple bond to make sure that everything had an octet when we only had 10 valence electrons to draw. To check your Lewis structures, it's a good idea to assign formal charges to each atom in a molecule. To do that, for each atom, count the electrons in lone pairs and half the electrons it shares with other atoms. Subtract that number from the number of valence electrons for that atom, and the difference is its formal charge. So let's look at 2 examples. We've got CO2, carbon dioxide, and in this first example, we know that oxygen contributes 6 valence electrons and carbon contributes 4. So that's this first line right here. The second line, we need to look at the electrons assigned to those individual atoms. That's just counting the electrons around them. So there's 4 electrons from the dots on oxygen, and there's going to be 2 electrons, 1 from each bond. So bonds are split up between the 2 atoms. So there's 6 on this oxygen and 6 on this oxygen, and only 4 on carbon, 1 from each of the 4 bonds attached to it. So 6 minus 6 is 0, 4 minus 4 is 0, 6 minus 6 is 0. That one's okay. Let's look over here now. Our initial numbers are the same because oxygen always contributes 6 valence electrons, carbon contributes 4, but the oxygen atoms are different. The oxygen on the left has 7 electrons assigned to it, and the oxygen on the right only has 5, 2 unshared electrons and 3 from bonds. When you subtract those, you end up with a formal charge of -1 on the left side and +1 on the right side. The correct Lewis structure is the one that has the formal charges at 0 or as close to 0 as possible. Sometimes more than one Lewis structure is valid, so let's consider ozone, O3. It's 3 oxygen atoms bonded together. Each one contributes 6 electrons, and there's 3 of them, so that's 18 electrons we need to draw. So 2, 4, 6, 8, 10, 12, 14, 16, 18. That oxygen isn't happy. We need to make a multiple bond. So I'll take these 2 electrons and move them over and make a double bond. Now I also, instead of taking electrons from the oxygen on the right, I could have moved 2 electrons from the oxygen on the left. Both of those Lewis structures are correct, and that leads us into resonance structures. Those 2 Lewis structures for ozone that we drew, there was a single bond on one side and a double bond on the other. That's not what we've actually observed with ozone. Double bonds are shorter than single bonds. So if an ozone molecule looked like our resonance structure, one side would be shorter than the other. However, when we've observed ozone molecules, the bonds appear to be the same length. So what that means is neither resonance structure is totally accurate. We use multiple structures, and we just call them resonance structures to describe the molecule. So the actual representation of ozone is somewhere in between these two Lewis structures. You usually have to draw all possible Lewis structures and you separate them with a double arrow like this. That means that the actual representation is a hybrid of these two. Sometimes there's even 3 or 4 possible resonance structures. There are 3 types of ions or molecules that don't follow the octet rule. The first type are ions or molecules with an odd number of electrons, like nitrogen monoxide, NO. 5 plus 6 is 11 electrons. The Lewis structure for nitrogen monoxide, the best we can do is something that looks like this. 2, 4, 6, 8, 10, 11 electrons. It's not following the octet rule because nitrogen doesn't have 8 electrons around it. Ions or molecules that have less than an octet, like hydrogen, can only have 2 valence electrons. Boron is also a special element. Its maximum valence electrons are 6. So we'd fill out the octet on the fluorines, but this is as full as a boron atom can get. And then the last type are ions or molecules that have an expanded octet. They can have more than 8 valence electrons. That's reserved for 4th period elements that have a D sublevel to store those extra electrons in. So we could have phosphorus pentachloride with 10 electrons around that central atom in the form of those 5 single bonds. Your question for this section: does the nitrate polyatomic ion require resonance structures to be drawn?